Good afternoon, everybody. I'd like to welcome you. My name is Mike Hoskins. I'm the CTO of Actian. 2005 was a watershed year for database technology. That was the year major analytic database projects were invented from scratch, understanding that the next 30 years are all about analytic workloads. Famous names like Barry Zane, Michael Stonebreaker, involved in those projects. We are very fortunate today to have another one of those names and leaders with us. Peter Bonch is one of the leading database scientists in the world. He's the inventor and founder of the Vectorwise next generation columnar analytic database technology, and he's going to talk to us about bringing that world's best of breed fastest database natively into the Hadoop ecosystem. He will be doing a brief book signing at 4 p.m. at our booth. Actian, we're one of the major sponsors. You'll find us in the hall. Turning it over to you, Peter.
Thanks, Mike. So, my name is Peter Bons, and apart from being a scientist, I'm also an advisor to Actian Corporation. Actian Corporation is the owner of my previous spin-off called Vectorwise. They sell this database system under the name Actian Vector, and I'm continuing to advise the Vector development team in Amsterdam. And today we are announcing a new product called Vortex, codename Vortex, which is the highest, the fastest, the highest performing, the fastest SQL in Hadoop system on the market as it comes out. So the talk is structured as follows. So first I will tell you a bit about Vectorwise, so the history of vector processing. So why is Vectorwise so fast and why has it been leading the charge for all these years? And then give you my perspective on the current SQL on Hadoop market, and then go into detail on what Vortex is. So the architecture of it all. Final slide is about benchmark results, and then go to the roadmap. Okay, so my earliest venture into database architecture is MongoDB, which was one of the very first columnar database engines directed at the analytical market, at the analytical workloads. And it's still thriving, actually. CWI distributes that in open source and continues to evolve it. This went back all the way to 1994. It really broke through, like Mike says, in the early 2000s. When we learned a lot about, I had actually another spin-off with MongoDB, we learned a lot. And then we started a new project called X100. And what's new in X100 is the vector processing model. So the same model that, for instance, Hive is now adopting in Stinger, and I will actually mention many other systems that are adopting this. So what is the vector processing model? Well, in a traditional database engine, a query like you see there, a SQL query like you see there, it selects people, employees, small with an age lower than 25, and compute some salary times tax, would translate into a relational query plan that consists of a scan, a select, and a project operator. And these are iterators, usually in an implementation, which have a next method. And the goal of the next method is to produce the next tuple. So the project calls next, and in order to provide the next tuple, the project then calls next on its child object, which is the select operator, and then on the scan. And the scan will actually read something and produce a tuple. This one is for a guy with an age of 40. So it's not selected, so select will call again next and finally get a tuple, and it propagates up into the, towards the top of the query tree. So this is tuple at a time processing. What vector processing is that you do all this, you do all query processing using vectors. So vectors are blocks of tuples. And one of the effects is that you have much less next calls, so much less overhead. So this reduces the interpretation overhead of database systems, which is very important for analytical workloads. So columns are like vectors. Vectors are like columns. So very often you see the combination of a vector processing and column store, and that is actually a very good idea. But the primary purpose of vectorized processing is not necessarily columnar storage. It is to have a representation of values in your execution pipeline that is simple arrays. And simple arrays are very friendly to compiler optimizations. So with simple array processing, the individual operators that compute something, so here you see the multiplication, so in this query there is a multiplication. I was multiplying the salary with the tax. So it boils down to very simple loops. And these loops, they get really optimized by current compilers, and they can really go blisteringly fast on modern processors. Because modern processors internally are highly parallel. They have SIMD instructions, but they have also many independent instructions that can be executed at the same time if the CPU finds independent work. And vectorized processing brings out this independent work to the machine, and that's why it becomes so much faster. I have no time to go into, let's say, the CPU and the computer architecture that's behind that, but it really works. So this research prototype became Vectorwise. Actian now, well, it bought my spin-off. It's now sold still as Actian Vector. And Actian Vector has been quite successful. It really shook up the market. Here you see a screenshot from a PhD thesis that shows the per thread performance of various products on the market, and Vectorwise really is a jump up in that these are TPCH results per thread normalized. So he says, Vectorwise is a new database system that has been designed from scratch to better utilize modern hardware, and that's fully true. And it really made a change. And now you see all the relational vendors, so the classical relational vendors adopting in one way or another columnar storage and vectorized processing. So Microsoft got a vector subsystem. In SQL Server, SAP HANA is another column store that uses vector processing. IBM followed suit with Glue. And recently also Larry Ellison announced Oracle in-memory vector and column option. But even though the industry is trying to follow suit, Vectorwise is still leading the charge in TPCH. You see actually in this screenshot, recent screenshot, that all the results that you find on the first page are Vectorwise results. So Vectorwise is the fastest single server analytical database out there. But we are here at the Hadoop Summit. Okay, and we have this tremendous wave of SQL and Hadoop systems and interest in providing SQL functionality inside Hadoop. One of the leading or the most adopted early lead in this market is, of course, Hive. And actually, we see that Hive is also trying to adopt these principles. So the Stinger release introduced columnar ORC files, it introduced vector processing, but there is still a large gap. But the ideas, they came from Vectorwise, and Vectorwise is, as I said, still faster than anybody else in this kind of workloads. So therefore, it's very interesting that Vectorwise is coming to Hadoop, and that is what Project Vortex is all about. So at the end of this month, it will be available, and this is a native integration of Vectorwise and Hadoop. Okay, I will talk a bit more about details later. So SQL and Hadoop is really hot, and there are all kinds of good arguments. Organizations are standardizing on Hadoop for managing their clusters, for writing cluster software. Typical Hadoop pipelines, they start with messy data, unstructured data, map-reduced jobs, trying to make sense of the data, cleaning it up. But what tends to happen at the end, what comes out at the end of that pipeline is less dirty data, so cleaner data, and less unstructured data, so more structured data. So the community is starting to realize that at the end of a big data pipeline on Hadoop, a SQL engine is a very valuable component. Okay. And also, if as an organization wants to have a large-scale data, a large-scale SQL system, is it really necessary to buy a separate MPP solution for that? If you already have Hadoop in your organization. Hadoop also is much more prevalent. It's becoming the standard. So skills to manage Hadoop clusters are much more easily found. So that's really the driving factors behind SQL and Hadoop. We think it's very important to align cluster software on Hadoop. And that's also why we did Vortex. Okay, so now there are many solutions on the market right now for SQL and Hadoop. And I kind of put them in 3 categories. Well, the first category is really not SQL and Hadoop. But there are many organizations who kind of push SQL solutions in connection with Hadoop, but they are not really running inside Hadoop. So I would call them SQL outside Hadoop. Examples are Teradata, Vertica, Oracle. There you see approaches where connectors are provided between, on the one hand, an MPP database system, and on the other hand, Hadoop. So to make it easy to copy data in and out. But copying data, of course, is not very handy, and also it doesn't make the IT infrastructure any easier, because now you have to manage 2 separate clusters still. Then there are other systems that I would call wrapped legacy systems, which typically take an open source existing database engine, most often Postgres or Derby, and then put a layer on top of that and put that on Hadoop. But there are 2 problems with these legacy-based solutions. One of them is that these legacy databases, Postgres or Derby or whatever, they tend to be older, and they stem from this split where you had analytical database technology becoming separate from from mainstream technology. So these are generic database technologies which are not optimized for analytical workloads. They're, in other words, slow. They are not vectorized, they're not column stores. Postgres is just slow. So if you put that as your workhorse in a SQL and Hadoop solution, the result is never going to be very efficient. Another problem with that is that if you're native on Hadoop, that means that all the data should be in HDFS. And HDFS is an append-only file system. And append-only is just not very friendly to existing relational database code bases. They always use in-place updates. So they just write in a raw data file or things like that. So it's just very hard to port Postgres natively to HDFS. So the only way to really do it is basically to switch off updates. So you see that solutions like Hawk, which is Greenplum, but which is again Postgres, they don't support delete, so you can't delete tuples and you can't modify tuples, because that would imply writing in place in HDFS. So these legacy systems have drawbacks, and of course, well, these are all legacy systems. So Hawk has Postgres, Adapt has Postgres, Citus Data also has Postgres, and Splice Machine uses Derby, also a row store, not optimized for analytical servers. And the third category I would call from scratch. So this is the right way to go. So you can say, okay, now that we know what the platform is, it's Hadoop, data should be in HDFS, you've played with Yarn, you can start from scratch and do everything right and design an analytical database engine. I think, for instance, Impala is an approach, and the Stinger release are honest attempts to do the right thing and to do efficient analytical database engines. The only problem, and I can tell from experience, is that SQL users expect an awful lot of functionality. So it takes years to develop a good optimizer. It takes years to develop an optimizer that can correlate complex queries, that can do internationalization, access control, security, workload management. So how do you schedule the resources if you have multiple ongoing queries, etc. Window functions. So it just takes a lot of time and a lot of effort to even meet the most basic requirements that SQL tools put to a database engine. So these from-scratch efforts, while you could say that they're promising, they're right now very immature, and they have years of development to go before they can really compete with existing solutions. So in this category, I would put Cloudera and Hive, but also like IBM's BigSQL and PrestoDB are definitely not mature SQL systems. Okay, so you can make the typical Mike Stonebreaker graph out of this. So on the one axis, we have got maturity. On the other axis, we've got Hadoop integration. So these red systems, they are very mature SQL systems, but they are totally not integrated with Hadoop. Then you've got these wrapped legacy products that are more mature from the SQL point of view, but they, for instance, can't do deletes and inserts. No, inserts they can do. They can do deletes and modifications of individual tuples. And they don't perform well because they are not analytical. And there are these from-scratch efforts that on the one that are properly targeted but very immature. And today, so Vortex is launched, which is a mature SQL language, and, which offers very mature SQL support, and is very well integrated into Hadoop. So I think that's very exciting. It's also very highly performance. I will show it at the back of the presentation slides that show results for the benchmarks that Cloudera is showing for Impala often, these DS subset, where they removed rollup and the other window functions. That they use to compare to other systems like Hive. But on those benchmarks, Vortex is like 15 times faster right now, out of the box on the standard Impala benchmarks. Okay, so what are the features of Project Vortex? Okay, it supports compressed vector data, the way Vectorwise has designed them natively on HDFS. So basically, Vectorwise plays really nice with HDFS because it doesn't do updates in place in the first place. This is the most efficient query engine. The Vectorwise engine is the most efficient query engine on the market. It's vectorized. It has been leading the TPCH benchmarks for years. And it's coming to Hadoop. It's easily configurable and maintainable because it doesn't have really tweaks. So it really, or configuration consoles, it really feeds off Yarn to know which nodes are available, where to run. If nodes go down, it uses the Hadoop infrastructure to relocate and migrate files. So it really fits into the Hadoop infrastructure and therefore is much easier to administrate than an MPP solution that requires specific custom tools to manage on a cluster. It has very high bulk load performance. We added partition table support to Vectorwise to do so. And it has very rich SQL functionality, including access control, analytical and windowing functions, and a broad set of SQL APIs, as you would expect from a mature SQL system. And it has a mature query optimizer. There was a lot of work put into here because Vortex is now, it's an MPP system, so it uses it's a shared, it uses all the different nodes of a Hadoop cluster. So we did a lot of extra development in making a distributed query optimizer. Okay, so there are also, this is what we are launching, but we are also working on other features, extra features. So one of the specific things we are working on is advanced HDFS instrumentation. So, don't do that. HDFS by default stores multiple replicas of blocks on, so 3 replicas by default on various data nodes to provide failover. Usually, the most systems don't care where these blocks are. Well, they know the default policy is that the node that wrote the file gets it locally. It gets the first local copy. But the 2 other copies of every HDFS block end up in random places in the Hadoop cluster. But there is a way, so it's possible in HDFS to customize that and to tell HDFS where to store the blocks. And this is what Vortex does. And you can leverage it then, basically to get always local data accesses. Also, if some nodes fail, you still get local access. And you can also use it for workload management. I will come to that later. Well, so Vectorwise uses, by default, its own vectorized and compressed column store format, natively stored in HDFS. But we are also working on accessing data that is stored in other and open formats on Hadoop. In the labs, we are also working, and it will be the first system for SQL and Hadoop. We are working on full update support. So the ability to do fine-grained updates, continuous fine-grained updates in Vectorwise. So there is a data structure called the positional delta tree. I will describe it in more detail later, that allows to do so, because Vectorwise avoids writing in place when updates happen. It actually writes to a separate differential data structure that causes very little overhead, because if you have differential data structures, whenever you query a table, you have to merge in the differences. So that's why the positional delta trees were designed to keep the cost for that very low. We're working on yarn integration, very deep yarn integration, which means that which goes even into elasticity, so that Vortex is going to be able to expand, to grow and expand in a Hadoop cluster, so that it doesn't take all the resources of a Hadoop cluster when that's not necessary. Okay, so it will take resources as necessary, and it will also only take resources that are claimed with yarn, so that other MapReduce jobs, for instance, don't interfere with the workload. And elasticity, okay, I already mentioned that. And I don't think that currently on the market, on the SQL and Hadoop markets, there are solutions that do all these things. Wow, you're really impressed. Wow, this is some timing. But so there are no people falling from the chairs, you know, when I say this. No systems that actually do fine-grained updates, no systems that do elastic resource management, and have this kind of deep yarn integration, nor actually this HDFS block placement control. So it's just not a straightforward port, Vortex. Okay, so now I will go a bit more, or even more into detail in the Vortex architecture. So when you connect to Vortex, you connect to a single front end that translates, that takes your SQL query and does a logical query optimization of that. And then the resulting query plan, the optimized query plan, is passed to the so-called worker set. So worker set are basically data nodes. It's a subset of the data nodes. I will show this here. So suppose that we have a Hadoop cluster. A Hadoop cluster, by the way, will not have homogeneous nodes. Some nodes will be more powerful than other nodes. I try to draw this here. So what you do when you install Vortex is you identify a subset of the data nodes to be the ones that Vortex may run on. Okay, we call that the worker set. And then your SQL applications, they talk through this front end to vector backend processes that are instantiated on all these nodes on in the worker set. Okay? And these nodes, they communicate with each other. So intermediate query results are exchanged point to point between all nodes. Okay, the data format are Vectorwise's native compressed data formats. There are things called min-max indices, so zone maps also that allow to push down predicates. I already talked about HDFS block placement, so we decide where the replicas go, and tables are either hash partitioned or global. So global means not that they are everywhere, but they are readable from everywhere. Data is in HDFS, so in principle every process can read any partition or any table. And below that, we use HDFS as the global file system. Given that HDFS replicates every partition 3 times, and these partitions are, thanks to our control, all in those worker set nodes, we can play with who is responsible for which partition. And this actually involves yarn querying to see where the blocks are. So when the system comes up, it decides who is responsible for what in a way so that all the nodes have preferably local partitions so that you get shortcut reads. So you never have remote reads in principle. So I'm kind of drawing this here. So you got global tables, the red things, or partition tables. And if you've got partition tables, then every partition in principle will be stored 3 times. That's what HDFS does. But we know where. Okay? And then it says there are HCFA block placement hints, that's what we provide. And you get these local shortcut reads whenever data is accessed. Okay, so we've got in storage co-located partitions. So the system exploits the fact that if you have a primary key and a foreign key and you partition on two tables, one on the primary key and the other on the foreign key, it recognizes that matching partitions are on the same node. Well, and therefore you can do joins without communication for those. You can do just local joins. Okay? So there is also special logic recognizing replicated tables or global tables, the small tables that are available for from everywhere. Because these global tables, because they're small, tend to end up in the buffer cache. This system has its buffer cache, unlike Impala. So you will get actually lots of caching for small dimension tables, and they will not take up network bandwidth. Okay, even supports clustered indices. So you get sometimes merge joins. You can get that in MongoDB. And min-max indices for predicate pushdown. And there has been lots of work in the parallel cost model, optimizing the way broad distributed joins are done. Distributed joins are either done by repartitioning both inputs, hash-based, or if one of the sites is small, using broadcast strategies, where the smaller table is broadcast to all the other nodes, depending on the size of the relationships. Okay? Same thing with group bias aggregations. There are different strategies for that. If you have many groups, you do hash partitioning. The query optimizer decides that actually using histograms. You get hash partitioning and then local aggregation, or if the amount of groups is limited, you do first local aggregation and then you re-aggregate the locals. So there are different strategies for all these resource-intensive database operators. Okay, Yarn integration. So we ask Yarn which nodes are less busy when starting or when enlarging the worker set, and choose a node that is not overloaded. So we get from Yarn those hints. We inform Yarn of our usage of the system, so that we prevent MapReduce jobs thrashing our performance. And what we would like to have from Yarn is the ability to do this dynamically while the process runs, because the database server will keep running. And the Yarn model actually allows you to set these resources only once. We currently work around that with placeholder processes. So we can increase and decrease placeholder processes, but in principle, Vortex is in control. But we are, of course, if and when Yarn supports dynamic resource management, then we will be the first to use that. Okay, the system also, this is, by the way, work in progress. And workload management, actually it says under construction. So the system attempts to monitor how busy it is, and then tries to be elastic, to see if it needs more resources or if it can do with less resources. And so it chooses the amount of cores and RAM for each query also. So if you have this expanding and contracting is not done on a per query basis, it's more gradual. But when a query comes, the system also does this workload management, so it decides how many resources to give to any given query that comes in. Okay, and elasticity. So here in the architecture picture, you see that, well, what's interesting here, you see that there is a big difference in Yarn footprint than the system can have, in theory. Because remember that every partition is replicated 3 times. It means that if you have 1/3 of the nodes, you have all the data. You can have all the data if you do this clever. So in principle, you could run queries only on 1/3 of the nodes and still have only local reads. Okay? And in principle, you can just run 1 core on that 1/3 of the nodes. That would be the minimum footprint of the system, but you could also expand it to use all the nodes and all the cores. And if you have, for instance, nodes with 12 cores, it means you can scale all the way from, you can scale a factor 36, because you can get 3 times more nodes and 12 times more cores. Okay? So these are many scaling steps that you can make with Vortex. This is not ready yet, but it is in the works. It's on our roadmap. Okay, so there is bulk loading. Nothing really, so there is a fast parallel loader, so loading is parallelized. There is also SQL Combine. This is a vector feature, so where you can actually load up delta tables and then combine them with existing tables. And we are also looking into, like I said, text and Parquet readers. This is not yet there. And updates, finally. So these updates, we aim to be able to support trickle update streams, so continuous stream of updates. Vectorwise is an analytical database system, so you should not think that by supporting trickle updates, I mean that this is going to be a good OLTP system, a transactional system. Better use HBase for that, probably. But what it means is that it can support situations where there are continuously arriving updates. Not bulk, but continuously arriving stream of updates. Not a million updates concurrently, but a single continuous stream of updates. That's what it's called trickle updates. And that's what what Vectorwise can do very well. And this functionality will be made available in Vortex. And with that, I think it will be the first SQL Hadoop system that offers that. So modify, deletions, and upserts use these positional delta trees. I actually have a picture of that. So if you have a table, in principle, you don't want to modify this table. This is actually a table. Well, this positional delta tree is described in a SIGMOD paper, positional update handling and column store. So if you want to know technology about it, you can read that. This table is actually clustered index tables. It's sorted on store and prod. So, and if you want to insert values in that, you actually have to insert them at the beginning because Berlin is before London. And so Vectorwise doesn't touch the table. It actually creates this tree, positional delta tree. The positional delta tree contains counts of how many tuples have been modified. Because the problem, if you identify updates by position, is that everything starts shifting. Once you're inserting something in the middle, then all the other positions change. And the positional delta tree allows you to get only logarithmic complexity in finding out these positions. Because every tree node keeps the current running delta of inserts minus deletes below it. So this is, it's described in the paper, and it allows a very fast data structure that can be merged very quickly, and on the other hand, allows you to really amortize and not do always in-place updates, but amortize the updates in this side structure, differential structure. Okay, so that was positional delta trees. So when things commit, Vortex writes to the write-ahead log. This write-ahead log is also on HDFS. So the failover capabilities of HDFS are fully leveraged to make this system safe. Okay, so and in principle, update streams to partition tables are just spread over all the worker nodes that update their respective partition. So it should scale, or it does scale actually quite well in the labs. Okay, let's skip over this then. Finally, here you see the DS benchmark that Cloudera published in January and put on GitHub, which we ran on Impala versus Vortex. And the results are, that Vortex is at least 5 times and at most 25 times faster on average, 14 times. The numbers fluctuate actually because we're still optimizing Vortex. It's not out yet, but it's significantly faster than Impala. So it's richer and it's faster. Okay. So I think SQL Hadoop is a really interesting space. It is where SQL, large-scale SQL processing, in my opinion, is going to go to in the next decade. There are a number of interesting young systems. I'm not going to take anything away from Hive and Impala, but these systems are currently simply not mature by SQL user standards. They have a long way to go. And they miss many features. Trickle updates is one, but there is a very long list. Query optimizer, authentication, access control, internationalization, workload management, all this requires a lot of work. So Vortex offers all of that right now. And it brings the fastest analytical database system for single server now to the Hadoop market. And that's pretty exciting, I think. And actually, we didn't do that just using a plain port. We actually tried to really look at HDFS and really look at Yarn to really exploit the opportunities, like exploiting the replication that HDFS does. This is the first in a database architecture for Hadoop that has been done, and also trying to achieve elasticity in Yarn. Because if the argument is that you're going to move your large-scale database system to Hadoop to kind of leverage a single large cluster environment and minimize the cost of administering that, then the database system should coexist with other applications, and that's where elasticity comes in. Okay, so where are we now? Well, this is the announcement. This is the first time Actian talks about Vortex today, and there is a preview edition available. It's not downloadable, but you can send an email to info@actian.com. At the end of this month, there will be an initial release. And in the fall, a second release that will have additional functionality. I talked about trickle updates, Yarn integration, HDFS block placement. This is all working in the labs, but it will be released in the fall. Okay, so if you're interested, you can learn more. You can visit the Actian booth, booth P6 in the Expo area. There is a technical white paper that you can get. You can see a live demo of Vortex versus Impala. So you can see that these numbers actually are real. You can meet the Vortex developers. Specifically, can you please stand up? Imported from Amsterdam are Adrian and Andre. So they know everything about Vortex. Actually, they started working on this very, very early on in 2012, and they wrote even a master thesis about their initial work. Not yet on Hadoop, but on using MPP features for Vectorwise. It's referenced in this presentation. You can also find that document on my homepage if you Google me. At the Actian booth at 4, there is also the opportunity to get a book. I co-authored with other researchers a 60-page text on column-oriented database architecture, really heavy scientific stuff, actually, technical. So you can get one of those copies signed, and you can get a big data t-shirt. So with that, I have just 1 minute for questions, I think. Okay, can you please walk up to the mic? Yes, yes. And, yes, so the question is if Vortex, when it will support trickle updates, whether they will be ACID, and the answer is yes. Yes, the same level of ACID as Vectorwise supports.
Where is your data definition and the stats and histogram state?
Excuse me, again?
Your data definition?
The,
is it all part of your files itself, or you have a separate system where you store your data definition?
the question is what our data definition system is.
Where it's stored. Where is your data definition stored?
Or where the DDL is stored. It is stored in the Vortex catalog files,
Okay.
which are also on HDFS.
Okay. Thank you.
Any other question? I'm out of time, actually. Well, if there are any other questions, then you can also post that offline at the booth. So thanks for your attention.